All right, naming molecular or covalent compounds. Remember, molecular, covalent is interchangeable. So a molecular compound contains molecules. So a molecular compound is typically a nonmetal and another nonmetal, and they share their electrons. They're actually connected, and they share 1 or 2 or even 3 electrons. And so a group of atoms that are chemically bonded together, their attractive force is just that actual sharing of the negative charged electrons. Now, a molecular formula has a completely different naming process than ionic formulas, and molecular formula naming is much, much easier than ionic. So you will be utilizing these prefixes that you can see here, and this list of prefixes will be provided for you on your equation page. So we have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, or deca, okay, depending on how many atoms there are. So I'm just going to dive into an example, and I think you'll go ahead and pick this up pretty quickly. So what we do here is no crisscrossing. We literally just read the elements, so diphosphorus, so that is P with 2 atoms of P for di, and then hexa, which we know to be 6, in chloride, and so it's basically this root word, which is chlorine, and hexa meaning 6, and the only thing we have to change is the ending of IDE on the second nonmetal name. Okay, so no crisscrossing, you just use the prefix of how many there are in the formula. So this is P2Cl6. Then we have sulfur dioxide. So sulfur and dioxide is dioxygens. Okay, now there is a specific rule, kind of an exception when you're naming molecular compounds. We never use the term mono on the first element. So even though this is technically a 1, you will not see nor will you write mono for the first element, okay? So I'm not even going to show this one. All right, trinitrogen, N3, hepta 7, so H3O7. So no crisscrossing here for molecular compounds. Now let's do the opposite here where we're naming them from the formulas, and I kind of already demonstrated that to you. The first element in the formula is named first, and we use that full element name, no changing of the ending. The second element is then named, and we change the ending to "ide." So we use prefixes to denote the number of the atoms present, and remember that exception I just told you about. The prefix mono is never used for the first element. So for example, to name a molecular compound, P3Cl5 is triphosphorus pentachloride. Okay? Let's go ahead and name these. So we have 4 S's, so we're going to go ahead and say tetra, sulfur. Now you do not have to capitalize any of this. I don't know why I've always done that. Usually everything should be lowercase. And then 5 is penta, and that is bromine, so it is bromide, IDE ending. Okay, so here's one of those exceptions where it's a 1, but we do not mention mono, so we're just going to go ahead and write phosphorus. It is wrong if you put mono on the first one, just so you know. And this is hexa fluoride. Okay, and then we have dinitrogen, tetra oxide. And then this is a good example because they're both 1s, and this is how I wanted to show you how mono is used. So this is carbon, and then there's only 1 oxygen, so we use mon. Now we don't write monooxide, it doesn't flow. We typically do not put 2 vowels together, so we're going to go ahead and just drop that O for mono and make it monoxide. Okay, so you may be familiar with CO, which is carbon monoxide. So we do use the mon to denote the second atom only having 1 atom of that type. All right, now we're going to go ahead and name acids. Acid naming is very similar to the ionic bonding naming, so you're going to want to make sure you have a polyatomic list available to utilize during this. So acids can be recognized by having a hydrogen in the front, and you can see a hydrogen right here in the front, and then also having an AQ at the end. AQ means aqueous. That means that the component that we're talking about is in water. It is mixed with water. So let me give you 2 examples here. If we have NaCl, which is just table salt, and we have an S, which is solid, and we have NaCl with an AQ, that is salt They're both table salt. This one is a solid form. This one is sitting and dissolved in water. Okay, so this symbol, this phase, tells you a lot about a substance. So to be named and considered an acid, it also has to be dissolved in water, hence the AQ. Okay, so to represent a mixture that is in water, we use that AQ symbol, and you can see that here. Now, sometimes if the label of a category is acid, you may not see the AQ on all the examples. I try to be pretty consistent with that, but if you have any questions, you're welcome to ask. So again, it has to have an H in front and an AQ at the end. Now, to name acids, there are two different type of naming ways. So if we have an H in front, which we always will, and then we have to kind of ignore that and focus on the next component. So the Cl by itself is a naming type without acid, so we're going to call that binary naming, acid naming. And then we have the root that is containing oxygen, which means it is a polyatomic, and that'll be on our next slide here. So an acid without an oxygen has the formula of the ide form, so for example, chloride, we're looking at HCl, really becomes hydro, and then this right here is the same root word, okay? So if it is chloride, the chloride ion, I actually made this a little bit confusing here, let's just say CHLOR, so it's chloride. So if it is Cl minus 1, such as it is in HCl, okay, this H is accustomed by this hydro word, this becomes hydrochloric acid. Okay, hydrochloric. So you look at what this component is, you name that, and then that becomes the name. So anything that is HCl, let me give you another example here, H2S. Now you're going to say, why does this one have a 2? Why did the HCl not? Well, keep in mind that H is joining with the Cl here. So let me erase this and show you this a little bit better. So H is always a +1 because it is in group 1. Cl is a -1. So when these join together, they crisscross and become HCl, and that's an acid. Okay, now when we're joining H and S, it's the H, okay, and the S, which has a -2 charge. So when we crisscross these, it becomes H2S. So this 2 or this 1 comes from the joining of the anion. So H2S, if we were to name it just as normal ionic naming, we would name it hydrogen sulfide, IDE ending. Anytime an acid has an IDE ending when you name it, okay, you name it hydro, so you actually write the word hydro here, and you write ic, and you write the word acid, okay, and then you replace that root word. So H2S with an AQ after is hydrosulfuric acid. All right, let's go ahead and try the other types of examples here. So we have polyatomic acid naming. Remember, anything with a polyatomic contains some sort of oxygen, and you do need to have your polyatomic list to be able to do this unless you have it memorized. So what we're going to really focus on is, again, that same component here. We're going to focus on the part that comes after the H, and then we have to be able to look at the part after the H and decide what the name of that polyatomic ion is. So just for example, this NO3, if you look at it on the periodic table, is nitrate, NO3, and you have to know there's an assumed -1 charge there. So because it is called nitrate, that is this rule, okay? If it ends in 8, you change it to ic. So instead of this being a nitrate, because of this H in the front and the assumed AQ, because we're talking about acids here, we actually change this to nitric acid. Now I want to show you the difference. That previous one was hydroic acid. This is just ic acid, okay? We do not put hydro if it is the 8 form of an ion. Now, sulfite would be, so again, sulfate is SO4 -2 charge. Sulfite is SO3 with a -2 charge. And again, you can verify that on your polyatomic list. Remember, when it's joining with an H, which is a +1, it crisscrosses, and you'd get this formula here. Because this right here, the anion is a sulfite, it is rule number 2 here, so anything with an ITE ending becomes an OUS ending. So the name of this acid with an assumed AQ here, or typically you'll see it, is sulfurous acid. Sulfurous acid. Okay? All right, so let's go ahead and try some practice problems. you can either do all the ones that are all the same if you like to kind of wrap your brain around doing the ides or the eights or the ites, but I'm just going to kind of work my way through. Now, what you will have provided for you on your equation sheet is anything that ends in ide becomes a hydro. Actually, you will not have this provided. I apologize. That's for intro chem. But what you do have to memorize is if there is an ide ending, which remember that means there's a charge from the periodic table, which is the column charge is +1, +2, +3, plus or minus 4. So if it ends in ide, it becomes hydroic acid. Okay, so remember this is the root word and right here is the root word. If it ends in ate, it becomes just ic acid, no hydro. And if it ends in ite, you change it to ous acid. Okay, that's an OUS. All right, so nitric means it is the ate form. So we're going to be using nitrate. It may help you to write what nitrate is. Nitrate is NO3 minus 1. If we know it's joining with an H always, that's a +1. Go ahead and crisscross, and you can go ahead and write HNO3 with an AQ. Okay? Now, because it has a hydro and an ic in the word acid, more so the hydro and the ic, we know that it is this first rule right here. So we're going to go ahead and just see what cyanate is, or cyanide is. So cyanide is just a CN minus 1. Okay, and I'm getting this off your polyatomic list. So what we're going to do is put an H in front of that. H is a +1, CN's a -1, so just HCN and a little AQ. Okay, so chloric acid is the same as the first one, so we're going to go ahead and use chlorate. Chlorate is ClO3 minus 1. Crisscross that with the H, which is a +1, and we get HClO3 AQ. Okay, acetic, okay, again is that same thing. So we're going to go on our polyatomic list. We're going to use the acetate ion. That's a little bit of a bigger one, C2H3O2. And acetic acid is actually the main component in vinegar. It gives it that, quintessential vinegar scent. So we're just going to go ahead and put an H in front. Now, some students will ask me, do I put the H with the H here? Do I just add it, or do I put it in the front? We're going to actually put it in the front always. That's what denotes it's an acid, is the front H. So that's okay that you're going to have multiple H's in different locations. So H, C2, H3, O2, and again, this is a -1 charge, crisscross. I'm going to go ahead and put that AQ. And remember, you do not need this part. It was just to help you kind of write it. Didn't erase there. Okay. All right, hydrobromic acid. So that is going to be the bromide ion with an H, and Br is a -1. So +1, -1 cancels. All right, sulfurous is right here, the ite form. So sulfite is SO3 minus 2. So go ahead and crisscross your H charge with that. So that's H2SO3 AQ. And then chloris is also the same thing. We're going to use the chlorite, which is ClO2 minus 1. We're going to put an H in front of that, HClO2, and an AQ charge. All right. Now we're going to do the opposite here on the other side. We're going to write the formula. So you're welcome to pause and try this on your own. So this is hydrofluoric acid. This is the phosphite form, so that becomes phosphorus acid. Remember that OUS ending. HCN is actually one we just did. We're going to call that hydrocyanic acid. Now, I will tell you, I probably made up some of these examples, so some of them may not be real, but it's still fine for practicing. HCl is hydrochloric acid. We will use that a lot in lab this year. All right, H2CO3 is actually the CO3 minus 2 ion, just so you know. Look that on your polyatomic list. That is carbonate, so it is an ATE ending, so it becomes carbonic acid. So remember, we replace the ate with ic, so carbonate becomes carbonic acid. You always have the word acid at the end of these. H2S is from the S minus 1 charge, and so therefore, or the S minus 2 charge on the periodic table means it's an ide ending. So we're going to call this hydrosulfuric acid. All right, and the last one we have is NO2. NO2 is nitrite. Because it is nitrite, it is this third example down here. It becomes nitrous acid. All right. So we're going to go ahead and look at how to name hydrates. Now, anytime you hear the word hydrate, if you're hydrating yourself, you know that it has something to do with water, right? And that is what a hydrate is. So a hydrate is actually like an actual salt crystal. It's a dry crystal that has water molecules already baked in there. And we call that weakly bound in there. So although it looks like a dry salt, basically like a sea salt, it actually has water molecules in there, okay? So the formula of a hydrate is written a little bit different. It has the ionic formula that you're so used to here, but it also has this dot, and this dot means weakly bound. So right here, weakly bound, meaning it is very easily evaporated, okay, which seems odd because it's a solid, but you can evaporate the solid and get rid of that water that is in there. So a hydrate is going to have this whole formula, the ionic compound name, the dot, and then the how many H2Os that are attached to it. Okay, so let's learn how to name those. So the formula is written with the dot before the water molecule. All right, so you have to have the ionic name, the dot, and the 5H2O. Now, let me just tell you the difference between hydrated and anhydrous. I believe we may be doing a lab, or you did a lab in Chem 1 or Gen Chem with this. Hydrated means that you have this water molecule weakly bound to it, so you're going to see this dot. Okay. Now, an anhydrous means the water is removed, and we do that by heating it. And therefore it becomes this. So it has the ionic solid, which is an anhydrous, and then it has the water, which has evaporated. Okay, so can you see the difference here? We have the plus sign, which means it's actually attached to it here, or that it has been separated from it, but it still exists somewhere in nature, and we have the circle, which means it's still attached to it. So an anhydrous in water is after we heat it, and it is a hydrate prior to that. Okay, now we can take this anhydrous and water and put them back together. We can just pour water on top of the CuSO4 and we can actually get back the hydrate. So it's very simple. We call that a physical change. So the naming is really not too difficult here. All you have to do is, again, name this ionic salt. So you'll have to use your polyatomic list. And then to name the water portion, you need to use the Greek prefixes that you will have access to. Okay, these are on your equation page. So it's kind of like a mixture of ionic and covalent or molecular naming. So we're going to call this one copper 2 sulfate. Now we have to know it's a 2 because sulfate is an SO4 minus 2 charge, and Cu is a transition metal, so it requires an unknown charge, so we need to use Roman numerals. Because there's no 2 shown, it has been crossed out, so that is why it is copper 2 sulfate. And then 5 indicates penta, and we just use the word hydrate. Okay? So let's go ahead and do an example here. A compound has the formula FeSO4, 7H2O. What is the name? So we're going to go ahead and do that same thing here. We have Fe. Fe is a transition metal, so you want to look up the charge of SO4. SO4 is the same as the previous example, is a -2, so therefore it has to be iron 2 because it crossed out. Sulfate. And again, you don't need the dot when you're writing the name. And then we look at 7. 7 is heptahydrate. Okay, so that is how you name a hydrate. You will see the word hydrate in there. So let's do the opposite. We have magnesium carbonate. So go ahead and write that formula and crisscross your charges. It has 2's that will cancel out. And then we have tetrahydrate. Tetra is 4. So here we go. We have a formula for a hydrate. Again, if you were to heat this up, okay, you would just end up evaporating that component and it would become